Welcome back to the lecture which is devoted to connecting equilibrium constant with molecular partition function. In the previous lecture, we started with an expression for the Gibbs function or Gibbs free energy, and we expressed delta G naught in terms of delta E naught and the molecular partition function as presented here in this expression. And then we were discussing that since delta G naught is equal to minus RT log K, we can equate the two. Once you equate the two, the new equation that I have is minus RT log K is equal to delta E naught minus RT log pi j q j m naught by Na Avogadro constant and raised to the power stoichiometric number. This equation can be rewritten as log K is equal to minus delta E naught by RT plus log pi j q j m by Na raised to the power stoichiometric number. If I can further extend this, as I can write log exponential minus delta E naught by RT plus log this product q j m naught by Na raised to the power stoichiometric number. If you carefully examine what I have done, that I have expressed minus delta E naught by RT as log exponential minus delta E naught by RT. Why I did was that I have a logarithmic function on the left hand side, and this is log A plus log B, which is equal to log A into B, and then I can get rid of the log on both sides. Keep this equation in mind, and from this equation I can write K is equal to product of Q J M standard state divided by Na stoichiometric number into exponential minus delta E naught by RT. This I am getting from the previous one. Log K is equal to log exponential this into this log A into B, and then you can get rid of the logs and you come up with this expression that equilibrium constant is equal to product of molar partition function under standard conditions for species J divided by Avogadro constant raised to the power stoichiometric number into exponential minus delta E naught by RT. Once again re-emphasizing that this stoichiometric number is positive for products and negative for reactants. Going back to your discussion in classical thermodynamics, equilibrium constant is a dimensionless quantity. And here if you now examine each and every term, you will see that the dimensions, the units, they cancel out, and equilibrium constant turns out to be a dimensionless quantity. In classical thermodynamics, you used to express equilibrium constant as the ratio of activities of the products and reactants. And here if you see this Na, which is included within the bracketed term, whatever is the stoichiometric number, this makes the entire thing dimensionless quantity. Therefore, in order to evaluate the value of equilibrium constant by using statistical thermodynamic principles, what you need to know? You need to know the molar partition function. You need to know the stoichiometry of the reaction. You need to know 0 point energy difference, and gas constant, temperature, Avogadro constant are anyway the quantities which are required. What we will do now is that this equation which we have developed is the same equation now written in a typed form, that K is equal to pi j q j m naught by Na raised to the power stoichiometric number into exponential minus delta R E naught by RT. Now we can think of applying this developed equation to the variety of reactions. The first reaction that I will like to discuss with you is dissociation reaction. X2 gas forming 2X items. Let us see, we apply to this. And in future I will avoid writing G because we are anyway discussing the situation in the gaseous state. All right. Now, our system is X2 going to 2X. So, we have to use this expression. So, K will be equal to, this nu J is positive for products and negative for reactant. For product it is plus 2. So, what I will write? Q of X m naught by Na this number, stoichiometric number is 2, and then I will have in the denominator for the reactant X2, that is Q of X2 m naught by Na. This is going to be for the reactant into exponential minus delta E naught by RT. Now, if you do the mathematical rearrangement of this, you get Qx m naught square divided by Qx naught for 2 into 1 over Na, because 1 over Na will come from excess Na in the numerator part, and exponential minus delta R E naught by RT. We have come up to this expression. That is easy so far. Now, when you talk about the dissociation reactions like this, then delta R E naught is twice the internal energy of X at absolute 0 minus internal energy of X2 at absolute 0. And what is actually this? This is X2 going to 2X. This is dissociation. So, instead of writing delta E naught, I can as well write dissociation energy at absolute 0 of XX bond. So, that means I need to have information on dissociation energy of XX bond. All right. So, going back to my expression, it was Q x m naught square divided by Q x2 m naught into 1 over Na was excess into exponential minus d0 by RT. Where from I get this expression? From this one. Qxm square over Qx2m naught 1 over Na exponential minus delta R E naught. This delta R E naught we have said that this is equal to D naught, and we have this expression now. Now, you carefully examine. The numerator is for X. X is an atom. The denominator is for X2. X2 is a molecule. An atom can have translational degree of freedom and electronic degree of freedom. There is no rotation and vibration in atoms. For molecule, there is translational degree of freedom, there is rotational degree of freedom, there is vibrational degree of freedom, there is electronic degree of freedom. That means for X, I will have Q translational of X and I will have Gx, which is the degeneracy of the ground state, electronic states. I require this information. For molecule X2, I will require Q translational for X2. I will require Q rotational for X2 because being a diatomic molecule, it can undergo rotation. I will require Q vibrational and I will also require the degeneracy of the ground state. I repeat, in the expression for K, you notice that the numerator is Qx square, where X is an atom. An atom can have translational degree of freedom and you also require knowledge of the degeneracy of the ground state. Why degeneracy of the ground state? Because electronic states are assumed to be or are far separated, so therefore their contribution is usually coming from the ground state term. X2 being a molecule, diatomic, you will have translational degree of freedom, you will have rotational degree of freedom, you will have vibrational degree of freedom, you will have the electronic term, that is the ground state electronic term, degeneracy of the ground state. Now with this information, what I have, I go back to this. K is equal to Q x m naught, okay. I am not writing because we assume it is standard state, this square over Q x2 m into 1 by Na into exponential minus d0 by RT. This is where we are. Now Qx m is equal to Vm by lambda x cube. Fine. And it will also have a contribution from degeneracy of the ground state. Overall partition function is multiplication of the partition functions. Qx2m is Vm, here I will put standard state, left hand side you assume as standard state, everything is actually under standard state, over lambda x2 cube into, I need QR, into vibrational into degeneracy of x2. What I have done is, I have included translational contribution, rotational contribution, vibrational contribution, electronic contribution. What we will do is, we will substitute these both Q's into this expression and let us see what it turns out to be. So what we will do is, let us put K is equal to Qxm square, that means Vm naught square by lambda x, it is a square, so raised to the power 6, into Gx square. Now divided by Vm naught lambda x2 into Qr x2 into qv x2 into g x2, and there is exponential minus d0 by RT. Molar volumes are same. PVM is equal to, you need to use PV is equal to nRT, or I will say P naught standard state into Vm, V by N is equal to Vm is equal to RT. That means according to this, Vm naught is equal to RT by P naught rather. This and this will cancel. So what we have, remember that there is one more Na term, and we should include that Na somewhere here into Na. I will just put here. So what I have now, K is equal to V, instead of Vm naught, I'll put RT by P naught into, I will put G x square into lambda x2, of course this has to be cube, divided by lambda x raised to the power 6 qr x2 qv x2 g x2 into Na into exponential minus delta E naught by RT. Next is use R is equal to K times Avogadro constant. So that means this R by Na, I can just use K. R by Na, use K, that is the K. This temperature is there, and Gx square, use this Gx square into lambda x cube divided by P naught is there. Then you have Gx2 is there, Qrx2, Qvx2 lambda x6 and into exponential minus d0 by RT. Now try to understand that how to arrive at this expression from this expression. The shape of this expression or the form of this expression is similar to that you used in chemical thermodynamics, because there also, what was it? Equilibrium constant was equal to the ratio of the activities of the products and reactants weighted by their stoichiometric number. Here also this actually is ratio. And how it is ratio is, since your reaction is x2 going to 2x, so it is qx square divided by qx2, and since each q is divided by Na, you have 1 by Na in the denominator, then exponential minus d0 by RT. Now after that you have to decide that the numerator and denominator, or for a given species, what type of contributions can enter in. If you are dealing with only atoms, then you will have translational degree of freedom, electronic degree of freedom. If you are dealing with the molecules, then the molecules, since we are dealing with the gases, you have translational degree of freedom, you have rotational degree of freedom, you have vibrational degree of freedom, and you have electronic degree of freedom. And we already showed that for x2 going to 2x, delta E naught is simply the dissociation energy. And this dissociation energy you can obtain from the 0 point vibrational energy. We will take up an example later on to show that how dissociation energy at 0 Kelvin can be calculated from the vibrational wave number data. But for the time being, remember that depending upon whether your reactant or products are atoms or molecules, you need to take their partition functions accordingly. Remember that the number of terms appearing here or in any of the expression is going to depend upon your type of reaction. Here we have taken a very simple dissociation reaction. There can be reactions in which you have atoms also, you have diatomic molecules also, you have triatomic molecules also, and you have multiatomic molecules also. And there can be more than 1:1 type, means there can be reactions of A moles of A plus B moles of B is equal to C moles of C plus D moles of D. That means you will have to account for the partition function of each one, A, B, C and D. Each one of them, that is A, B, C or D, can either be simply an atom or it can be a diatomic molecule, it can be a triatomic molecule, it can be multiatomic molecule. The examples include, for monoatomic you have just ideal gases, helium, neon, argon, etc. Diatomic you will have carbon monoxide, nitrogen, Cl2, I2, etc. Triatomic you can have water and similar other molecules. Carbon dioxide is another diatomic molecule. Then you can have multiatomic molecules. So the situations can become more and more complex as the number of atoms involved in a molecule increase. Therefore, you will have to very carefully decide how many terms and which terms are to be included in the denominator or are to be included in the denominator. We will discuss this in more details when we take specific numerical problems, and then I will explain to you that when you are using a particular formula, when you are using a particular expression, whether it is allowed under those conditions of temperature or not. But all those we will discuss in the next lecture. Thank you very much.